Dijkstra's algorithm is not new. It was conceived by computer scientist Edgar Dijkstra in 1956 while working at the Mathematical Center in Amsterdam. It was originally constructed to demonstrate the capabilities of a new computer. The aim here is to visually present networks and shortest paths through them. I want to utilize what we learned throughout the lectures and labs in this course, especially what we learned about D3. Having done a data analysis project for the midterm, I wanted to try a different type of project. This idea came to me while working on the labs about visualizing networks with D3, and looking at a subway map to find my way in the city. When Dijkstra conceived this algorithm, his objective was to choose a problem as well as an answer that non-computing people could understand. He designed the algorithm for a transportation map in the Netherlands. How does it work? First, pick the unvisited node with the shortest distance from where we are. Calculate the distance through that node to each unvisited neighbor, and update the neighbor's distance if smaller, and then repeat. What makes Dijkstra's algorithm significant, and more generally finding the shortest path, is its extensive utility to graphs, and that it is applicable in every domain where networks and complex systems exist. Shortest path has applicability in many well-known areas. For computer scientists and engineers, one of the first thoughts that may come to mind is routing packets through computer networks, but there are many more areas that we use this concept every day. Finding the shortest path really means finding the most optimal path. In a network, when we want to get from A to B, we are looking at the cost of each path. That lowest cost path may be one hop away, or maybe many hops away. There is no shortage of examples of visualizing Dijkstra's algorithm on the internet. I spent time looking at about 15 different implementations. 3 of the best ones, in my opinion, will be showcased based on demonstration of the basics and visual appeal. David Gallies of the University of San Francisco produced a web application which visualizes the execution on randomly generated graphs. To get this application working, you need to identify the starting node and then click Run. You don't specify a destination node, so this implementation will go and find the shortest path from the starting point to every other reachable node. I like the animated execution and the tabulated results. The ability to step is helpful when trying to closely watch how the algorithm works. Lisa Veldin produced a really nice web application that is a comprehensive learning experience. It provides explanations with visuals and interactive graph exploration. Graph editing is straightforward. You can easily add and remove nodes and edges, and even change existing values. When running, you select the starting node and it finds the shortest path to all connected nodes. The animation here is also very nicely done, as is the graph editing. I also like that you can upload and download the graph definitions. The last example is Graph Online. The visual elements here are not as pretty as the prior examples, that's just my opinion, but it has some nice features. Adding nodes is straightforward in Graph Online. I found adding edges a little clumsy, but workable. Graph Online provides several algorithms to choose from, and not just those to find the shortest path. The zoom in and zoom out is a really nice feature, especially if the graph is really large. The selection of algorithms makes this application usable beyond finding shortest path. There are so many good resources available online. Conway provides a practical example. There is a graph overlaying a map of Santa Barbara. Select a starting point and let it run. You can hover over destinations to see the shortest path. There are some very good resources on the web, and it is easy to derive ideas and motivation. None of the examples provide everything that I was looking for. That's good, right? Now that we know about Dijkstra's algorithm and we've seen some existing visualizations, let's dive into the project work. There's a lot to get through. Most of the motivation for this project comes from my interest in graphs and networks and how much I've enjoyed learning and working with D3 in this course. But in order to move forward, I needed to do some exploration, so let's take a look at that. I learned about Dijkstra and shortest path in a class during my undergrad study. I remember implementing the algorithm in Pascal on a VAX minicomputer. I don't have that old code or textbook anymore. Jupyter Notebook proved again to be a valuable tool. I quickly adapted Giles Bertrand's code into the notebook environment and was on the way to learning and exploration. What I like most about the notebook environment is how rapidly you can develop a small amount of code and how quickly you can see results. It also makes it very easy for using different datasets or modifying an existing dataset for the same algorithm. At the outset of this project, I envisioned doing everything in the notebook environment first, and then adapting that work into a D3 implementation. However, getting to interactive network visualizations in Jupyter was not easy. Matplotlib and NetworkX are good at what they do, but they are not quite the solution for interactive network visualizations. Some searching online discovered Viz.js2 Jupyter, a really interesting project for network visualization. The group at UC San Diego wrote a great blog entry on the topic of interactive network visualization in Jupyter. Their use cases are in biology. This package is mature enough to help me make good progress, and got me much of what I was looking for. The examples provide the necessary framework for figuring out how the tool works, and you can adapt it for your own needs. They even published some very good documentation. I expect to be looking at this package again in the near future. Learning and exploration in the notebook environment was time well spent. I was able to apply this effectively, which reinforced my learning and solidified my understanding. The next stop is building a web application with D3. This is not something that I have a lot of familiarity or experience with, so it still seemed like a big hill to climb. I started with a long wish list of things I wanted to accomplish. Recognizing time constraints, I was able to narrow down this version 1 to some of the most important items which would make the application usable. Deciding on data formats has always seemed important to get right. The network JSON format used in class seemed very sufficient, so I opted to go with that. The example network used during the notebook exercises was small, simple, and effective. Each pair of connected nodes have directed edges to and from each other. Giles Bertrand implementation was so straightforward, and the closeness of Python and JavaScript syntax made porting Dijkstra's algorithm fairly easy. My D3 web application is pretty simple. That was one of my user experience objectives. It could use some prettying up eventually. Here, we load the network definition from file and use D3 in force layout to visualize the network. The goal of my application is to find the shortest path between a source and destination node. We select a start node and an end node. Click Compute and the results are displayed visually and in tabular form. I'm not a web application developer yet. This was a good first project that was not overly simplistic. I learned quite a lot during this process about JavaScript, D3, and visualizing networks. What's next for my application? I would like to give it a much more complete user experience, and I would like to add more network algorithm capability, inspired from some of the examples showcased earlier. In closing, I must say this project was a lot of fun, and I learned a lot along the way. And I'm really optimistic and excited about my future career in this space. Thank you for watching.